Welcome to Aerospace Engineering. Today we're going to talk about atmosphere in Unit 1.2.4. So we're going to talk about what makes up the atmosphere and how it works and how we use this in aerospace engineering. So when we're talking about the atmosphere, we're basically talking about the envelope of gases that surrounds the Earth. So it's a mixture of gases. 78% nitrogen, about 21% oxygen, about, and 1% other stuff like argon, carbon dioxide, things like that. Bottom line is it sustains life on Earth, protects us from the solar radiation. So when we look at this thing, it's really a thin sheet, about 60 miles thick, and that's defined by what's called the Kármán line. Just a physicist came up with the point where you can no longer use conventional flight mechanics. There's not enough atmospheric particles to generate lift or control. So now you're in space flight using only thrust or inertia to control your flight path. So that's what we define it as. It's not like the atmosphere magically stops at that point. It just becomes less and less. 75% of the Earth's atmosphere is in the first 36,000 feet, meaning that most of the gas particles are in that first 36,000 feet. We, of course, live at the very base of it. Those particles create pressure, and we'll look at why. But the weight of all that gas pressing down or being pulled down by the gravity of the Earth is what actually creates atmospheric pressure. So as we sit here, we're under around 29.92 inches of mercury of pressure, about 14 psi in that ballpark, pounds per square inch, or what you're used to living in. So the other thing it does is absorbs radiation, and what it does to absorb radiation is it prevents a lot of harmful light energy in the form of radiation coming through and basically burning you up, and mutating your cells and destroying you. It also retains heat. Now that's good and bad. Portions of the Earth's atmosphere retain too much heat. That's what we refer to as global warming when we get things like a lot of carbon dioxide or a lot of methane in the air. It retains more heat than it normally would. So the Earth's atmosphere is a heat retainer as well. Now if it didn't do that, when the sun went away, we would get very, very cold very, very fast. But it acts kind of like a blanket and stabilizes the Earth's temperature. Now, where is this line that forms the edge and basically defined it as not enough atmosphere to fly? Well, if I look at it to scale, this is kind of what it looks like. And it's kind of like a piece of plastic wrapped around a basketball. So if that's our 4,000 mile diameter, roughly, Earth, that's shown in green there, the atmosphere is that little blue line, and it's pretty dinky. So we kind of got to zoom in on this, and there's a zoom in on it. And that's our Earth's atmosphere. And what I did was that little triangle is to scale. That's Mount Everest. So you can see that when we talk about the Earth as a smooth ball, it really is. When we look at topographical relief maps that have got like the little bumps on them or a globe, they're grossly out of scale. The Earth is very, very smooth overall relative to its diameter. The Earth's atmosphere is very, very thin relative to the Earth's diameter. So that Kármán line, that's basically where we divide it from space to atmosphere. So the white outside of the blue is space. If you want to be an astronaut, you got to cross that line. Different places define it differently, but generally it's about 100,000 feet, about 60 kilometers out. So, sorry, 60 miles, or 100 kilometers. I had that backwards. Okay, so the Earth's atmosphere comes in layers, and we talk about this in layers because the layers, the different portions of them behave differently, and they behave differently because they're comprised of different amounts of gas. And most of what we're going to talk about here is this first layer, because that's where all the weather is, in the troposphere, and the troposphere goes up and then is separated from the stratosphere by basically a level called the tropopause. It's kind of an artificial creation, but it is a definition of where the stratosphere starts. So we go up from the troposphere, As we cross the tropopause, we go into the stratosphere. That's this next layer up to about 160,000 feet. So we don't do a lot of flying in that layer above 36,000 feet. We do a little bit up into the mid 40s. Most airplanes, though, won't fly above 40,000 feet. Most commercial airplanes, most fighter jets won't do that either. A few airplanes, specialized airplanes like a U-2, will fly up in the 80, 90,000 foot range, but they're rare. Not really any traffic up there. So all of our weather's happening down in that troposphere. When we go above the stratosphere, we're in what's called the mesosphere. So the mesosphere has a unique thing where it starts getting cold again as you go higher. And then as you move up into the thermosphere, you're now approaching outer space. It gets warm for a while, and then it dramatically gets colder as you go out into outer space. Now, it also depends a lot on whether the sun is shining or not when you get up above that thermosphere. So those are the layers. We're going to focus almost exclusively on the troposphere. Now, if you look at the diagram over here to the right, you're going to notice that that first layer, that troposphere, is not uniform. And that is not an accident. The troposphere is influenced by the heating and cooling of the Earth. So as the Earth spins around, the equator is always closer to the sun than the poles are. For that reason, the warm, moist air around the equator creates a thicker troposphere down towards the equator. So here's another picture of the same thing and what kind of goes on in this. And you can see almost all of our flight occurs down here, the very bottom of it. It's both in kilometers and miles. It's not in thousands of feet, though. You'll see the temperature goes down generally as you go up until you get above about, I'm going to say in the 50,000 foot range. It stabilizes all the way up until you get really high, and then climbs, descends, stabilizes up there. So you can see what goes on. Our flights occur down here in the down in the lower layer, the troposphere. That's where all of the flight's going on. Rockets and space flight is happening up here in the mesosphere and thermosphere. That's when we start doing a rocketry. So that troposphere is not uniform. If you go to the polar region, your troposphere is going to be pretty darn low, 8,000 meters, where it's going to peak out about 18,000 meters when you get down to the tropics. Now, that's why thunderstorms down in Florida have really high tops. They'll get into 50,000 feet. A thunderstorm up in Canada is not ever going to get to 50,000 feet. Or if it did, it would be a humongous storm. It may peak out at 30,000 feet because there's just not the atmosphere to support that. So it's a little bit different as you go up towards the poles. So thicker down towards the equator. So in the weather, one of the major weather conditions we talk about here are the winds. And these are caused in the troposphere largely by three different things. The first one is a convective currents, basically convective pressure flows from low to high, or from high to low rather. And those are called Hadley cells when we look at those in the troposphere. And they exist and they're relatively static around the Earth. The other thing is local features, differential heating, sea to land, plains and mountains. Those create winds. Then the third one is the Coriolis effect. The Earth spinning creates its own wind, but not the way you'd think. So let's look at pressure variations. When we talk about pressure variations, we just mean localized high or low pressures, frequently seen on the map. So this weather map. Now these localized high and low pressures can be predicted by a region in the Earth, and we'll talk about that. So some regions have them. Also some regional events will flow and move, like a hurricane moves across the Earth's surface. That's a regional low. So those pressure variations, we get anywhere from about 980 millibars to 1,020 millibars of mercury. That's just a way of expressing how much the pressure is. There's not a lot of variation there. If you look at the 40 millibars or 40 over 1,000, a very small percentage of variation creates all of our weather. Now those pressure variations create a high pressure. A high pressure is defined as denser, colder, less humid air. So if you look at the map, the highs are over the plains. The lows are down here where it's warmer and more humid because of water vapor. So the highs have generally falling air columns because the air is dense. The denser air falls. The lows are hotter, more humid air. They're rising air columns. So if you look at a cloud on a hot summer day and you'll see it boiling up, that's where you're physically seeing the rising air column associated with a lower pressure. Now the convective winds are created from the outflow from a high to a low. And in the northern hemisphere, they typically flow clockwise around a high pressure, anti-clockwise around a low pressure, or counterclockwise. So when we look at these pressure isobars, these can tell us the way our winds are going. So our winds are approximately flowing on that pressure isobar in a clockwise manner, and approximately on this pressure isobar in an anti-clockwise manner. So that's how we predict our winds. They typically flow from high to low. So if we know where the pressure variation is, we know which way the wind's going to blow. That's how we can predict that direction of the blow. Now, fun fact, the larger the pressure gradient, the larger the winds. That's why, as an example, when we talk about a hurricane, and the eye wall of the hurricane has some of the most severe winds because that's where the largest difference in pressure occurs. So the larger pressure gradient makes a faster flow, which is manifested as a larger wind. So I talked about the feature of the Earth. Basically, the Earth's atmosphere, the tropopause, makes perpetual highs and lows all the time. And these are called Hadley cells here at the equator. And all that it says is, hey, at the equator, I pretty much create a perennial high or a perennial low pressure right here at the equator, which pushes warm, moist air up. That warm, moist air flows and cools as it goes further north away from the sun, and then makes a resulting high pressure right here. This high pressure air falls and it's drawn back towards my low. My next cell, my mid-latitude cells, create the same thing, and the polar cells create the same thing also. So the net result is we get winds that flow typically in a direction. So we have southeasterly trades, northeasterly trades. Now you'll notice that the flow direction is opposite from the northern hemisphere to the southern hemisphere. By pressure variation, it really isn't opposite. The direction it flows is partly because the Earth is spinning from left to right, so it gives it a Coriolis effect. These winds converge at basically the tropics down around the equator. So those Hadley cells always create similar weather patterns. So we live in a desert. The desert is caused by a perpetual high pressure system that sits over the southwest United States. Occasionally, that high pressure system gets pushed to the side. We get monsoonal flow. Humidity comes in from the east. Or in the winter, we get a winter flow. Humidity comes in from the west, the southwest, down in the Mexican, down there in the Pacific Ocean, down off of the Baja, Mexico. So our winds and our weather are reasonably predictable based upon this idea of pressure differential. So the winds are also made by surface features, local surface features. And the bottom line here is the geography of the local environment creates an uneven heating. And that uneven heating makes pressure differentials. So if you look at one like a sea breeze, if you've ever been to San Diego, and you'll notice, wow, the wind is always blowing off the ocean. And the reason for that is if you go inland just a few miles from San Diego, it's hot and dry. That hot air absorbs some of that humidity off of the ocean, and it absorbs it, makes it a little more humid. It then rises and flows out over the ocean, is cooled, falls, and then flows back inland. So you get a perpetual sea breeze when you're close to the coast. That only works within a few miles of the coast. Another one is if you're by a mountain. So the weather on one side of a mountain is very different than the weather on the other. In fact, you can have completely different, you can go from a tropical environment to a near desert environment on the other side. And an example here is an Catabatic Flow, and that just means that I've got warm surfaces and the heat is rising because of the warm surface of the mountain. We see that in Arizona quite a bit. We live in a valley, so you'll see thunderstorms build around the valley perimeter, and that is the mountains around the valley heating and rising, and then the coolness of the rising air making the clouds. We can also get a Catabatic Flow, which is essentially a cold surface like an Arctic surface or the Rocky Mountains in the winter can cool air and make it fall down to the ground. So one was rising air from the mountain, one was falling air from the mountain, a cooled mountain versus a hot mountain. There's many, many more of those. So our local surfaces that are uneven heated create pressure differentials and airflow as well. So when we talk about air pressure, we're really talking about how much does the mass of the particles that are above you push down. Now, at sea level, we talked about around 14 pounds. It's 14.7 pounds worth of air particles are pressing down on you per square inch. In other words, every square inch of your body has 14.7 pounds of pressure on it, or force. And that force is made up of all of the air particles in the atmosphere above you at that point. We talk about a standard day as 14.7 psi or 101.3 kilopascals. That's the metric version. And it just says that that column of air, 60 miles tall, that's 1 inch by 1 inch, weighs 14.7 pounds, or 5.5 kilograms, another way to think of it. So that's what standard day means. So you can imagine that if I go higher, the density of the air is higher and the pressure is higher. So on this graphic, so here's an air column, and I've just made an arbitrary air column, and I'm down here towards the bottom of it. And what you'll notice is the air at the bottom is dense, and all of the air above me is pushing down on me. So that's that weight. Now, as I start to climb, what happens is two things go on. There's less air above me, physically. There's less above me, more below me. And that air that is above me is also less dense, so it exerts much less overall weight, resulting in less pressure. So as I climb, the air gets less dense, and I have less pressure. Those two go hand in hand with the ideal gas law, although that's a very difficult law to apply in the atmospheric conditions. Now, those air particles that are above weigh less overall, and that results in a decrease in pressure. So as I go up, the pressure reduces. We talk about standard atmospheric conditions, and what we mean by that is a standard day is defined as 15 degrees centigrade at sea level and 101.3 kilopascals of pressure. It also means 59 degrees Fahrenheit and 14.7 psi in the imperial system. Now, we simplify an atmospheric model. There's a lot of variables that go into what makes the density of the air, variables such as how much humidity is in the air. So a lot of times we'll talk about a standard day at 50% relative humidity. In other words, the air is holding about 50% of the water vapor that it physically could. So humidity we don't take into account in this model. Now, if we were to look at the Earth's atmosphere, and we're going to go out and we're just going to go to 10,000 feet, but this extends out pretty close, the same relationship all the way to 36,000 feet. And what we would see is a relatively linear lapse rate. And that lapse rate, or that decrease in temperature as I climbed, is 2 degrees centigrade per 1,000 feet. So if I start out at 15 degrees centigrade at sea level and I climb 2,000 feet, I should have gotten 4 degrees colder, or 11 degrees centigrade. So this is true when we're in the troposphere. What goes along with that is my pressure is also relatively linear. It's not perfectly linear. It's relatively linear. And this just says I lose about 1 inch of mercury pressure. The weight of the atmosphere goes down linearly for every 1,000 feet up. So if it's 29.92 inches of mercury, a measure of pressure, it's 19.92 inches of mercury at 10,000 feet. So that idea, both temperature goes down as I go up and pressure goes down as I go up, is important. Because in the Earth's atmospheric model, within the troposphere, we can now build a mathematical relationship that's very straightforward. And that mathematical relationship has 2 components. The first one says that the temperature in degrees centigrade goes down. So 15.04 here is our measure of temperature at sea level, standard day. And then every meter I go up in height, h, I go down 0.00649 degrees. So the temperature goes down. It's important that you understand this temperature measure is in centigrade. Now the pressure goes down, not quite linear. Remember I said it's kind of linear? It's actually to the 5.256 power. You're like, huh? Yeah, that's what the model is. And this just says that I start out at 101.29 kilopascals, standard day at sea level. And now, as I go up in altitude, my temperature goes down. So my temperature at altitude, this is a conversion factor right here to go from degrees centigrade to degrees Kelvin. So centigrade to Kelvin. So I plug in my temperature at the altitude that I'm at, and I can arrive at the pressure at that same altitude. My pressure always decreases. If you were to add a standard day here, sea level, 15.04 degrees onto this, you would see that you get 288 degrees Kelvin. This factor would be 1 then. So the pressure at sea level would be 101.3. So that's all those two are doing, is they're relating temperature to altitude and then pressure to temperature, which indirectly relates it to altitude. And we'll build a spreadsheet for that. Now, the atmospheric conditions, the air density basically is altered based upon pressure and temperature. And generally, as we go up, the density lowers, the temperature lowers. That's a general rule of thumb. So here is my density. The density is a function of the pressure measured in kilopascals, and then this thermal constant, which is measured in temperature. Now notice again, I'm taking temperature plus 273 C to convert it to degrees Kelvin. Degrees Kelvin. So that's important. We're in temperature, degrees C in all of these formulas. This density ends up with a unit of kilograms per meter cubed. So rho, if I want to find my density and I know my pressure, I can find it by looking at the temperature at a given altitude. So pretty straightforward, although a rather complex looking equation. We'll look at several examples in class. So when we talk about basically the atmospheric conditions, and remember I showed you Mount Everest in our atmosphere, and it looks like a little bump on the surface of a giant Earth. Well, really, most of the Earth's atmosphere is below you at that point. It's very similar to the altitude that a jet flies. That's a C5 on a refueling boom. Fun fact. Hard to breathe up there because guess what happens? There's less particles, meaning there's less oxygen, and there's less pressure pushing that oxygen through the membrane of your lung to put it into your solution in your blood. So they typically need to use supplemental oxygen. Pilots flying up there either need a pressurized cockpit or they need supplemental oxygen. If you lose that, you're done. So you can have a leak in the fuselage, or you could have window failure, lots of different reasons that you could lose that pressure. But there's just, first of all, not enough oxygen, and second of all, not enough pressure to push the oxygen into your bloodstream. So you suffer from something called hypoxia, which we'll learn about later on. So we need supplemental pressure. Now, the other reason that airplanes don't fly above 40,000 feet generally is because the pressure differential required is really high. So if you go to 100,000 feet, you need to have a tremendous pressure vessel to hold in the difference between the outside pressure and the inside pressure. Now, we also care about the atmosphere because it has a fairly large role on our aircraft speed or how it flies. And you can kind of you can kind of figure that out from your life experience. And if you run through air, which is a fluid, there's far less resistance than if you ran through water, which also is a fluid. One is a gaseous fluid, the other is a liquid fluid, but the density of the two are different. So our airplane flies differently in different density of atmosphere. So when we look at the aircraft speed, that's one of the manifestations. And what happens as our airplane flies through it, as you learned when we introduced the first idea of lift, is that the air molecules move around the airplane, and what you're looking at is a shock wave image of an airplane. So looking at how air is flowing around, and it creates its own pressure waves. Now, the air compresses above about 250 miles an hour, and as that air compresses, it gets more and more compression until you get close to the speed of sound. As your airplane begins to go faster than the speed of sound, it goes faster than the pressure wave is moving. That creates a shock wave and a sonic boom when that happens. So this prior picture right here is actually an F-18, and you'll see there's two areas of the airplane that have a pressure that is faster than the speed of sound. One is at the tail, the second is right behind that cockpit on the canopy. So that's what going faster than the speed of sound means. So when we talk about aircraft speed, we can talk about it as the speed of sound. We can also talk about it as true airspeed or indicated airspeed. So those terms, true airspeed means how fast you're really going. Well, that means how fast am I going across the ground beneath me. The Mach number is how fast am I going relative to the speed of sound in the air mass that I'm flying in. And the third one is indicated airspeed. And that's essentially what does my speedometer in the airplane read. And that speedometer in the airplane really reads dynamic pressure. It reads the pressure of the air pushing against the airplane. So as you can imagine, as the air gets less dense for the same speed, I get less pressure. And we can look at that in a chart, and I can say if I fly at 200 miles an hour, or knots, whatever I want to call it, indicated on my dial at the surface of the Earth, I'm going about 200 true miles per hour, or Mach 0.26. When I start to climb and I keep going that 200 indicated airspeed, my air is less dense. So in order to get the pressure that indicates 200, I'm really going a little faster. I'm going 215. And my Mach speed relative to the speed of sound, I'm going 28% of the speed of sound at that point. That keeps going on, and you can see I go all the way to 45,000 feet. I still am reading 200 on my dial, but I'm really going 434 miles an hour with an indicated Mach 66% of the speed of sound. So you'll see that these go up as I hold the same indicated airspeed. So there's a comparison available between indicated, true, and Mach. Well, we talk about Mach a lot because it is essentially an altitude stabilized true airspeed that's easy to use. So that Mach number is a decimal representation of the true speed of sound in that air mass. So if I say I'm going Mach 1.0, it means I'm going as fast as the speed of sound. That speed of sound at sea level is 761 miles an hour. So it kind of takes that variability of what my indicated airspeed is out of the equation. Now the speed of sound changes with the temperature, and what happens as I go higher and higher, it gets colder and colder. The speed of sound decreases as it gets colder. So the Mach threshold is lower also, but still going Mach 1 at 25,000 feet means I'm going the speed of sound at the temperature that's at 25,000 feet. So when we talk about Mach numbers, we can talk about subsonic. That means you go less than Mach 1. An example of a 737 that you may fly on for Southwest Airlines, it cruises at about 0.75 Mach. Still moving pretty fast. 0.75 Mach is 500 miles an hour, a little more, at its cruising altitude. So you're moving pretty fast. Now supersonic, between Mach 1 and Mach 5, is like a fighter. F-15 top speed was theoretically 2.5 Mach. You'd burn all the fuel the airplane had to get it there. Very difficult to achieve those high supersonic speeds of Mach 2.5 in most conventional fighters. Some planes flew that speed all the time, like an SR-71 flew at Mach 3 cruising, but flew very, very high. Hypersonic is between Mach 5 and Mach 10. So as an example, if I went Mach 5, I could fly from LA to New York in 38 minutes. It's kind of hard to imagine those kinds of speeds. You're literally flying across Arizona in under 5 minutes from corner to corner. So very, very fast. But hey, there's even faster. High hypersonic, Mach 10 to Mach 25. At Mach 20, you go around the world in about 98 minutes, around the whole world at the equator. So it's very, very fast, and that's kind of the speed that you look at of things re-entering the orbit is the high hypersonic, the 25, Mach 25. We don't have anything that flies at that speed right now, but high hypersonic is typically associated with objects re-entering the Earth's atmosphere. Still faster than the speed of sound. So that's the relationship between our atmosphere, pressure, winds, speed. Remember those formulas that we looked at. Everything is in degrees centigrade. All our heights are in meters. And we can derive our density based upon the lapse rate for density, which is actually the lapse rate for temperature. We'll work some problems next. Thanks for watching.